In this video, we'll discuss exponential models. Now, an exponential model is a relationship between two quantities, and what happens is one increases, the other value increases exponentially, so it increases at a much faster rate. So we have a standard form which is y equals a times b raised to the x plus c. Now, each of those parts, the x and the y will be our variables, and the a, b, and c will be numbers within this equation. And what we're going to do is recognize that the base of our exponential component, the b value, has to be greater than 0 and cannot be 1, because if it's 1, we just have a straight line. Now the a value is the initial amount of the quantity in real-world problems, and that's going to come into play here in a little bit. So let's look at some components to this that are important to recognize. When we're looking at growth means that base has to be greater than 1, and that's when we get those very sharp curves upward. Whereas if it's between 0 and 1, it cannot touch 0, it cannot touch 1, that's when we get our exponential decay, which you hear a lot about with radioactive isotopes. So let's look at the idea of, well, how do we graph this? One, we can always use our calculator to definitely help us with this, and remember that we have the caret key on there to help us create the exponent key if you can't find the exponent key on your calculator. So if we want to graph it manually, we're going to use a table to help us. So let's try to graph 2 times 3 raised to the x. So I'm going to just choose a couple values to help me get started for x. So I'm going to go from -3 to +3, and I'm going to solve this at each of those cases. So in the first one, it'd be 2 times 3 raised to the -3. When this happens, I want to make sure I do my exponent, then multiply. And that will make this become 2/27, which is about 74 thousandths. I'm going to do the next one. Again, raise it to the -2. I'm going to take my exponent and then do my multiplication, which gives me 2/9, which is about 222 thousandths. When I do -1, that's going to end up with 2/3. 0 is going to give me 2 because 3 raised to the 0 power is 2. To the first means it's going to be 2 times 3, which is 6. When I do it to the second, I'm going to end up with 2 times 9 is 18. And then to the third, 3 cubed is 27, so I get 54. Here's where that exponential growth starts to happen that we can see. So if we take these points and we plot them on a number line, you can start to see that really fast curve, and then you can see, well, how do I create that? And you can double check that again using something like Desmos. Now we can also solve problems that use exponential modeling. For example, here, suppose Sharad placed $2,000 in an investment that increased his investment at a rate of A equals 2,000 times 1 300ths, all raised to the t minus 1, where A is the amount in his account and t is time in years. And the problem says, after 13 years, how much money will be in Sharad's account? Well, the key to start with is, what's our formula? And then what information do we have? In this case, we have the 13 years, which is our t value. So now we can simplify our expression here to get the total amount in the account. So 13 minus 1 is 12, so I'm going to raise this to the 12th, then multiply by 2,000, following our order of operations. And that will give me about $2,851.52. That's what will be in the account after 13 years. So in other words, it gained about $851 in 13 years. Now we also have the natural exponential function. That's where instead of putting a number for our base, we use the letter e. And it does have an actual value. It's called the Euler number, and it has an approximate value of 2 718 thousandths. And it's an irrational number like pi, it goes on forever. But we're going to say that we can use that e key to help us. Now, if you're having trouble finding it on a calculator, look for the natural log button as well, because they're inverse operations. X and y are still our variables, and a and c are going to be numbers as well, just like the other form. So here, let's try graphing e to the x plus 2. We follow the same thing. We're going to use -3 to +3 just as a way to help us keep track of what we're doing. And here we do e to the -3. We find that e button on our calculator, raise that to the -3, then add 2. That's going to give us approximately 2 and 500ths. Then when we do -2, that'll give us approximately 2 and 135 thousandths. See, it's just a very small change. As we get to -1, that's going to get us to 368 thousandths. When we get to 0, that's going to take us straight to 3 because e to the 0 is 1. And then when we do to the first, we now start to see these jumps happen. When we do the second, we're going to, again, larger jump up now to 9 and 389 thousandths. And then when we do to the third, e to the third is going to get us up to 22 and 86 thousandths. So you can see slow progression, and then it gets faster and faster in its growth. So if I take these 7 points and plot them, I can then see what is the graph of this exponential function. And again, use Desmos or use your graphing calculator to help you with this. Now we also see population growth and decay occur within populations in nature. Bacteria, viruses, animals, even radioactive decay are all following exponential growth models or exponential decay models. It's a very common thing that we see. And sometimes those will then turn from exponential growth or decay into logarithmic growth or decay. There's a very close relationship there as conditions change. So if we are dealing with exponential growth, we can follow some formulas to help us out. Now, the one we're looking at is very specific in that it is assuming continuous growth or decay, so at the rate at which we're talking here. So when we're looking at this, our P on the left side, that's going to represent what's the amount after some time has passed. P naught, that's how we say that, is our original amount of a population. What's the size that we're starting with, or what's the amount of material that we have to start? K is our growth rate. This is often going to be in some small value. If it is looking at populations, we often may have the birth and death rates, and we need to subtract them to get that rate. And the last one is time. And often time will tell you whether it wants it in a very specific time, minutes, months, years. Oftentimes you'll see this commonly in years, but it's not always just in years. And again, remember, we use this with continuous growth and decay. So let's say that in 2020, the US population was 320 million people with a projected continuous growth of 0.59%. If maintained, what will be the population in 2050? So some key parts, we start with our formula. We say, okay, population in 2050. That's what the new value we're looking for. Do we know that? No, that's what we're trying to solve here. So we're going to keep P. That's the unknown in this equation. The next one says, what's our initial amount? Well, that's the population in 2020. Well, population 2020 was 320 million people. So that's what we're going to use for P naught. The next part is our K value. What's the growth rate? Here it tells us it's 0.59%. But remember, we have to change that to its decimal value. So we're going to divide that by 100. So we're really looking at 59 10,000ths. And then we need time. Now, here's what you have to pay attention to. What year did we start? We started in 2020. We're looking at going to 2050. So our question is, how much time has changed from 2020 to 2050? And that's 30 years. So now we have our parts. We can substitute them into the formula and start to solve. Start with your exponent. We're going to multiply the 59 thousandths 10 thousandths times 30. And then we're going to do e raised to that value, and then we multiply it by the 320 million. Now your calculator may or may not shoot out a full number. Oftentimes it'll do this e to the 8. And we've talked about what the e means. That means 10 raised to that value. It's in scientific notation. So if we want to take our scientific notation and change that back into its decimal form, we'd say that that's about 381,962,000 people in 2050. So the population is looking to grow almost 61 million people in 30 years. Now let's look at one last problem. This time, let's look at birth and death rate problem. So in 2019, West Virginia's population was about 1.8 million people. The birth rate was 10 and 2800ths births per 1,000 people, and the death rate was 17 deaths per 1,000 people. if this trend continues, what will be West Virginia's population in 2032? So again, let's start with our formula. We're going to assume the continuous growth or decay. We look and say, what we're looking at as population 2032? We don't know. That's what they're asking us in this problem. So that's going to be our P. Then we look and say, well, what's the initial population? That's what it was in 2019, which is where we started, the 1,800,000 people. Now to calculate our rate, here we have a birth rate and a death rate. And the rate is 10 and 2800ths births per 1,000. The per 1,000 means it's 10 and 2800ths divided by 1,000. And the 17 per 1,000 means it's 17 divided by 1,000. We're looking at two fractions here. So we can change them to their decimals and subtract them. And we see we actually have a negative death or a negative rate here, which means that the population is actually decaying over time. Very slowly, but it is decaying. And the last thing is time. Well, look at the year we started. We started in 2019. We're going to 2032. So we're looking at what's the difference between those 2 years, which is 13 years. So now we put this all together into our formula. 1,800,000 times e raised to our negative rate times 13. We're going to multiply here, do e raised to that value, multiply that by 1,800,000, and then we have our new population. And if we look at what that is approximately 1,649,425 people. So they're dropping about 150,000 people in 13 years.